episode 20, a big milestone for machine learning seminar at Helmholtz-Zentrum Gestacht, and our last Christmas episode of 2020. We've covered a lot of different interesting papers over the past year or so. We've seen different techniques, different data sets, different research aims, and they've been mainly conceptual pieces showing what could be done in kind of toy scenarios or thought experiments. And I think what's really nice to end the year right now is a paper where we're actually getting to apply this to something a little bit closer to an application where we can say we're actually predicting useful things and we can imagine using those things right away. So our paper today is on sea level prediction. It connects to a lot of previous ideas related to in-painting, related to GANs, related to interpolation, related to convolutional networks. We are very lucky to have the first author, Zegou Zhang from the Hydrodynamics and Data Assimilation group at HZG to present this paper for us. Zegou is a PhD student who started in 2018, and he's combining machine learning techniques, which he's going to tell us about, with oceanographic data. He's really interested in data analysis with ML for ocean and atmospheric systems. So with that, Zegou, I'm going to turn over to you if you want to share your screen.
Yeah, okay, I will try to share the
1 second.
screen. Okay.
I need to stop my share 1 second. I'm having some issues. Apologies. I'm having some Zoom issues on Linux. Oh boy. Okay. No. Apologies, ladies and gentlemen. We are having some technical problems.
No, I can't.
Please wait 1 minute. Okay, and we are back. Do you want to try to share your screen now?
Let me try. Yes, good. Seems like. Wait for a moment. Okay.
Great.
Okay, can you see mine?
Yep, see you, hear you. Great.
Okay. Hello everyone, my name is Zegou Zhang and I'm a PhD student at HZG, and now today I'm going to present our paper in a brief way and be quickly or easily understood. And the name of our paper is the sea level variability. The rest of the signal is like there's more. I think there are small non-linearity because the rest signal are usually maybe perhaps driven by the wind or pressure gradient. It's more non-linearity for this low frequency signal. And for the whole for the four signals CSI, maybe it's more easy to reconstruct because we have two different tasks.
And the data you're reconstructing, the target outputs, which you're trying to produce with your GAN, these are results of data assimilation with a physical numerical model. Is that correct?
Yes, the target data is from a numerical model simulation.
I see. Which means
But
it's
just I want to add
please.
what is very important here. They don't assimilate. This is an operational model. So we take model which is used for the Northwest European shelf to forecast the sea level, temperature, etc. But this model assimilates only surface temperature and salinity data, and it does not assimilate the sea surface height from satellites, for instance.
Well, that's very interesting. So the model, by assimilating salinity and temperature measurements, it's able, by solving the dynamics and physics, to come up with a good estimate of the sea surface height.
Yes, because North Sea is a relatively simple system. It is first shallow water. It is driven by wind. It is more or less two-dimensional, so it is not extremely complicated as like adding system of the open ocean.
I see. Okay, thank you. So I hope that answers your question, Eduardo.
Yes, thank you. So basically, the low frequency is the let's say the signal in which the tidal oscillations have been filtered out, basically. Am I right? Hello?
I can hear you.
Can you repeat what did you say?
The question was, is the low frequency signal a signal in which the tidal oscillations have been filtered out?
Tidal oscillation, oh, we just feel like...
The answer is yes.
Okay, thank you.
2 days window.
Yeah.
It's enough.
Okay, then here we have two figures, but for the North Sea, the figure on the left is M2 tide, mainly with also tidal gauge observation overimposed with circle symbol in Fig 1. And for our model, for our GAN model, we actually use this 19 tidal gauge points as input, and then we use the entire North Sea 2D field as target to train the model. The figure on the right is the low frequency signal, C-subtype signal, the room square error of the low frequency subtype signal. And for the low frequency C-subtype signal reconstruction task, we also use the same input data format and the same input output target into data format. Well, here is this structure, generator structure is for the 465 signal 2D map reconstruction. And it's similar like a U-net structure, which is very useful for image segmentation and for pixel-wise image segmentation. So we select this one and make some small changes to achieve our task, to achieve our C-subtype 3D map reconstruction tasks. Well, this teach about the discriminator. It's a very simple structure. Actually, we only have several convolutional layers, and where the loss function of this discriminator is cross entropy together with L1 and L2 loss for distinguish with the reconstruction and the real target. Actually, for both C-subtype and low frequency C-subtype, we are using the same discriminator. Well, for the generator. This page is about the generator structure for low frequency system surface height 2D map reconstruction. Because we did before we established this structure, we did many experiments, and we also used our previous U-net structure. But we feel because I think the low frequency signal is more nonlinear, and actually, so we established another new generator structure to achieve this task, and by using this generator structure, and we can make a reasonable reconstruction. And again, and for these two different tasks, we are using the same discriminator, but the generator structure is different. We have two different generator structure. For about the training data set, we use 1 year hour data, and then use another 3 months data, 3 months data from another independent years. Time resolution is hourly, and all the data set is from a numeric model, M7, and another high resolution numeric model, GeoCost, together with tidal gauge observations. And for the quality evaluation skill score, we use index agreement, the gradient here, and this index of agreements could provide this approach to compare model prediction, and that is GAN output, and with observation. The observation is that is AMM7 simulation outputs. Now, actually, if the index value is 1, it means that we got perfect agreement. We got perfect reconstruction. If the value is 0, then we got bad reconstruction.
So this is an interesting index to me. In some ways, it's like a correlation coefficient because it goes between 0 and 1, but in some ways it's not, because you have to have the right scale, the right units on your outputs to achieve 1 here, whereas for a normal Pearson's correlation, you wouldn't have to have the right units. This is a common index for evaluation? What made you choose this?
We also use room square error, and this index agreement usually we just want to measure the GAN model performance. Yes, actually, to show whether the GAN model is capable of reconstructing the reasonable CSSI signal with.
Okay.
Yeah. I hope this table is about our experiments, and actually we did many experiments by using different data set on training and testing phase by using our GAN model actually. And well, this table actually is about the detail, because we have several figures, index agreement figures. Actually, we did about 10 experiments using, you can see that using Dataset from either from M7 model or from GeoCost or from real TGA, but also target dataset. We see that the target dataset is the real one, are from the same model, numerical model M7. And during the experiments, we changed the different different training input and testing input to check the GAN model performance, and by using the index agreement. Well, this figure is about skill score figure for reconstruction quality on testing data set. I see we use as I said before, we use 3 months from another independent years test data set to test our GAN model reconstruction. And those 10 figure is corresponded to the preface page. And for the detailed values, I calculate the mean and value of the index agreement for the entire North Sea. This the mean value of some is the reconstruction results compared with the RM7 model targets. And we can see that if we change the different data set to train and to validate our model, we will have different agreements. And here, this we draw some conclusions that if we use all the data set from the same model, it seems like we could get better reconstruction results. And if the training or testing data set come from different models, like if we use a real observation as testing input, and we use only the numerical model M7 dataset as training input, then we will got different index agreement. So we draw some conclusions that we use 19 tidal gauge station observation to make this reconstruction, and from the index agreement, it seems like we could get reasonable results. But the second conclusion is more important, I think, because from the experiments we did, it means that it demonstrates that the dataset agreement or the consistency between the input and target of the machine learning model is very important for the reconstruction quality. Because if we use this, if all the data set is from a same model, and we use data set to train this and validate our model, we could get better results. If the data set for training and testing the model from different resources, the index agreement will be damaged. The third conclusion is that from this paper, we demonstrate that machine learning could be used for some machine dynamic variable reconstruction with only fewer prior knowledge. Here I see prior knowledge is we only use like 19 points from a 2D matrix. From 2D matrix, we only have several points data available. For the rest of points, the data points is 0. And then the GAN model usually cost low computational resources, which could be a potential tool for dynamic analysis. And then that's all. Thank you.
Thank you very much. That was a really interesting presentation. I know I have questions, but let me open it up to the Zoom chat as well as the YouTube chat. If anyone has a question, please go right ahead. While we're waiting for questions, let me start with one of mine. So, how did you choose this particular architecture, this particular U-net and discriminator and generator? Did you try other ones? What was the process that brought you to this?
Considering how I chose this model, because this idea actually comes from some very creative references I also list here. Here we can see we have a cloud structure reconstruction using generative adversarial networks. We have also another brief paper about physical space, satellite image reconstruction problems actually. So from those references, which stimulates me about if we use this kind of U-net structure for the CSSI or some other variable reconstruction, it could be practical. So I tried this U-net directly first. But yes, we have tried several another models, but until now, what I could find is this U-net work could be useful and it works for CSSI signal reconstruction. Yeah, with only few prior knowledge.
I see. And Mika Silver asks, what was the resolution of the sea surface height data?
What do you mean? Do you mean the spatial resolution or time
I
resolution?
assume both. Both. Would if I remember. Hourly data and the spatial resolution?
Spatial resolution.
The spatial resolution is 7
7
kilo.
Oh,
7
kilometers.
Because we use
So another question I had is I read in here. Oh, go ahead. I'm sorry. There's a question from the chat. Please, Eduardo.
No, I have a question or a few questions. First, regarding to your discriminator on slide 7. Because in the very end, you say you have like 4 by 4 by 512 filters. And if you apply this now with a 1 by 1 convolution, don't you get like a 4 by 4 by 1 output?
4 by 1. What do you mean? Could you repeat that?
If you have this 4 by 4 by 512 convolution, now apply 1 by 1 kernel to it. Don't you get
flatten? We still have a flatten layer to make it into a 1D, 1D vector for the cross entropy loss.
Okay.
Yeah.
I see. And
because I did not add that too much information here because it is just a simple,
All right. Okay.
explanation.
So again, probably it's the same issue in slide 8. You say it seems like you're using 2 units, one after each another, like.
Yeah, no, it's not. It's different. Can you see? It's different. The second one is similar like U-net, but for the course network, it's kind of different.
Yes. How did you do the upsampling in the first unit? Because in the second unit, you're using deconvolutions, right? That's this fractional strided convolutions.
Upsampling.
Okay, so you're using once upsampling and once you use transpose convolutions.
Yes, you're right.
Why did you choose different upsampling techniques here?
Because we test several times for our tasks, and I found at last this structure works. Maybe there will some other structure will works also. Maybe it works better than ours. For our experiments, I did several experiments to achieve this task, and it seems like this structure works for the CSSI reconstruction. Yeah.
And you didn't provide any noise to the generator, right?
No noise. That's a very good idea, I think, because actually, if we add some like Gaussian noise, maybe we could get better reconstruction results. Because our input, we only have like several few points data. Actually, for CSSI signal, it's very simple signal. If we introduce like salinity or temperature, I don't think it's enough. 19 points is enough for the reconstruction. I think you're right.
Right.
Your question is very very nice for stimulates me about thinking about introduce.
Yeah, thank you for your answers.
Yeah, thank you.
And so I have one more general question, which is how good is the target data? How good are these estimates of sea surface height? If I look in the manuscript, I see that there is the agreement between them and the tidal gauges is maybe within 1 meter, maybe anywhere between, let's say, maybe 16 centimeters to 50 centimeters, depending on the location. If I look in your table 1, so what are the limitations of these products, and could we actually train again to do something better than the AMM7?
Better, yeah, maybe then if we want from these experiments. Well, actually, I learned something actually because if that you see if we can get better results, I think we can. The problem is about input. Because we only use like several 19 points. I don't think it's enough for getting better results right here. Because if we like use maybe more data points in the whole area.
It's possible that maybe adding more tidal gauges would help, but if the limiting factor is the quality of your target data, then you really just need more.
Yes.
I mean, what would be also interesting is if you, suppose you had 30 gauges, right? And if you used maybe...
You're right, the target data.
You could use maybe some of them as input and some of them as testing. But in the end, you'll still need some kind of 2D field to train on.
Yes.
It's an interesting question.
Yes, the data set is very important, actually.
So in the introduction, you mentioned that there are these satellite altimeters, but they don't work very well near the coast. Can you talk more about what are their advantages and disadvantages? Why don't they work near the coast? And what kind of coverage do they really provide?
Maybe I
coverage. What do you mean? Do you mean the numeric model?
Well, I mean, if you look at the data provided by one of these satellite altimeters, I imagine it can't be in every location at every time, so it provides coverage over the maybe part of the North Sea at different times, depending where the satellite is? Or maybe you can explain this to me, because I don't know.
So maybe
where is satellite?
This question. First of all, we have one picture, one coverage of the entire basin once about 1 week. So with the tracks which cover the North Sea, you cannot resolve, let's say, the most important signals, which are the tidal signals. This is one problem. The second problem is that when satellites approach the coast, because of many technical reasons, the quality of the signal worsens. So it is well known and checked for many other regions in the world that satellite altimetry is good for the open ocean and is not good for the coastal. And the third, what we did with Zegou was to try to see what are the useful signals for the North Sea extracted from the satellite altimetry. So Zegou did some tries to reproduce his analysis just using tidal gauge data and satellite data. And it did not work well at the high frequencies because actually the tidal signals, the satellite signals can well resolve the long-term periodicity or variations in North Sea level, but they don't well resolve the short-term variability. So these signals for the North Sea are relatively useless.
That's very interesting. So it seems like the only really 100% solid ground truth data here is the tidal gauges.
Yeah. Yes.
Yeah, it is right. And you can just take the model as a generator of the ground truth and play with the model and see what you can reach with it. But there is no ground truth from the point of view of observation. This is a big problem.
And if you go to the open ocean, I'm sorry, go ahead.
Maybe it was a very short explanation which Zegou gave about using different combinations of data to get good or bad emulation of sea level signal. And the problem is that if the data come from different origins, you just try to marry the tidal gauge data and model data, it does not work very good. Although visually, if you compare the data, even if you do some statistics in the locations of tidal gauges, the differences are not so big. So the one conclusion from our study was that it is very important for the success of these neural networks or whatever machine learning is to use consistent data sets.
I see.
It's not a big problem.
Huh. Well, but so if I look in the open ocean where there maybe are not tidal gauges, is there any way of measuring the high frequency component of the sea surface height?
This will come soon. You know, they prepare the new mission SWOT. It will be a satellite which has much better capabilities in comparison to existing altimetric data. So with these new SWOT satellites, maybe you will be able to cover with better precision the small scale variability and higher frequencies. So
okay, thanks.
this will come soon.
More questions from chat. Did someone have their hand up before?
If I may, I would have one or two questions. Hi, everybody. Marcel here. So my first question was regarding going a bit more in the direction of these different data sets. So if you look at the table that you have of the different experiments that you ran, exactly. So you have different training inputs and different training targets. One thing that I found interesting is that for both training and testing, you always use the AMM7.
Yes.
So my first question was, is it possible to train on G-code data?
Yeah, that's possible, and of course it's possible. We just select the M7 output as a target. We can also, the data set is free of selecting. You can change if you want. So here for our experiments, we just use the M7 outputs as a real one, as a target. Yeah.
Okay. A related question is for testing then. So even if you trained, say, let's look at the, even if you trained training input and training targets AMM7, one thing you could try is when you then test with G-coast tidal gauges, these 19 points, you could also evaluate on the G-coast fields, like compared to them. Is that correct? Or is there a problem with resolution?
No problem about resolution. We can mix that. You mean we should have another, comparison, by using different data set?
Okay, because what you would expect is that if the tidal gauge, these 19 points from G-code is different from M7, if you put something different into the neural network, then also the answer should be different. So it's not necessarily wrong if
you're
there's
right.
a difference in network answer because there's a difference in network input, right?
Yeah, you're right. Exactly right.
Maybe I can interfere a little bit. We did exactly this, if I understand your question. So the target data is always the same, but the input data would be different. And we did several experiments. One is using as an input the AMM7 data. Second is using GCOS data. And third is using, during the training phase, the same data, the MM7 or GCOS data. So you just prepare a new model. You train the model with non-consistent data set. And if this data are put in the training phase, then the performance is much better, which is similar to the issue of data assimilating by weighting errors in the model and in the observations. So when you train with inconsistent data sets, the system tries to adjust these inconsistencies and to minimize the error.
Yes. I think I get that. So if I look in the last two rows of the table here, J and K, this is what you're describing, and this makes a lot of sense to me. Just for H and I, the two rows before that, I would have suggested if you train on AMM7 to predict AMM7, then you could also, on top of the test you already did, try to predict G-coast output from G-coast input. And from what I understood, this would be possible and would be an interesting thing. Because I think in machine learning, this would be generalization tests that are more common than this, even though this also has its value.
Yeah, right. Yeah.
And then the second question, if I may, in the paper, you talked also about a control model that you ran, a Kalman filter, that seemed to give overall very similar results to the GAN results that you here presented today as well. Could you comment on what you found? How the two methods compared? What was the advantage of using a GAN? Where did it fail?
Here's the problem.
Maybe I can answer this question.
Sure. Yeah.
So,
Yes.
we wrote in our paper, in the discussion part, the following. These comparisons of the skills of different methods depend very much on the type of data you use. So this was our experience when we tried to use the same GAN model for emulating the sea surface temperature or sea surface salinity. If you have relatively simple signal, which one example of this is the sea level, then you can, with relatively low number of EOFs, simulate this signal rather well, because Kalman filter used in our model, in our paper, uses EOF analysis. So if you, with several EOFs, can well replicate the signal, then good. Then the Kalman filter can beat the machine learning. However, if we have much more complicated signals, like sea surface salinity in the coastal area, then Kalman filter, which uses some kind of Gaussian concept of this linear operator, it has some problems. And for these specific cases, machine learning or GAN method, which Zegou uses, seems better than the Kalman filter. So there is no kind of a simple answer to your question. The answer has to be done if you do consistent simulations or analysis of many different types of data. And this is one task which we will be addressing perhaps further in the next months.
If there's no more questions, I want to ask one last question. Anyone who still has one, please chime in or write in the chat. And the last question I want to ask is, what about application?
I have another
Oh,
question.
please. I'm sorry, Toby. Carry
regarding
on.
more to
Carry
the
on.
paper as well,
Mhm.
because you explain your GAN loss that you use, especially for the generator, and you are not only using the discriminator as a loss, but you use other loss terms as well, like an L1 loss, an L2 loss, and even
Yes.
something else. How did you choose these losses? Like, why didn't you just use the discriminator loss?
The loss was we combine this L1 and L2 loss on the together with the cross entropy of generator part. For the discriminated part, we didn't change. It's similar. It's same like U-nets and like the classical GAN loss. The loss the new here we just change the loss for generator to different generator. For the reason for I chose L1, L2 is because, here the reconstruction task is pixel-wise reconstruction. L1 is, mean absolute error could be used for the reconstruction. L2 is root mean square error, which could be smoother to the field actually. And also before I chose this, I add these two loss to the generator. I also did many experiments. Because at first I just used classical GAN without change anything to test our task. It does not work. So from some references, I think perhaps it could be helpful if I, just add the mean square error and the root mean square error to the generator. And it seems like, from the results, it seems like it works, but it's not perfect. Yes.
Right. Did you try?
It's not perfect. Yeah.
Did you try training on only the L1 and L2 loss and just not using a discriminator at all?
Yeah. Maybe you are right. Actually, yes. It's not right now. Our model is not perfect. Yes. To be honest, I am sure it's just still more improvement space for improvements, and perhaps we can also use like just U-net without a discriminator.
Yeah, I was thinking that because you're not using a noise anyway, so that
Yes.
sounds really like a unit task. Yeah.
Yes, and another thing, you see the noise. I think it's very useful. Like Gaussian noise is to the field. If we introduce, if we add those noise to the input, and perhaps we could get different results. Yes, for the reconstruction.
Yeah, thanks for your answer.
Welcome.
Okay, any more questions? I have one last question, but anyone else have?
So,
anyone else, especially someone who hasn't asked a question before, please go jump.
A question about the structure or the potential usage of U-net or GAN. Because also, I'm also a newer, machine learning students. I'm also trying to establish or learn some use for a better structure for machine usage.
Yeah, I'm really working with GANs at the moment as well, and I can see the difficulties in training a GAN without additional losses. So you have to really search a lot for hyperparameters and stuff.
Not only hyperparameter, you need to take, a lot of time if you use more data, more data sets. But the reality is, I know actually, sometimes it's collapse. Hyperparameter, linear rate, the batch size, and the convolutional kernel size. And here's another problem is, another idea is about the convolutional kernel size. For our task, we only use the 3 times 3 kernels. I think maybe if we enlarge the kernel size, the result maybe would be better or not. I'm not sure.
Right. I don't know if there are any other questions, and if David is still here.
Yeah, I'm here. Can you hear me? Oh wait.
It doesn't seem like it.
Apologies. I think I was having some audio problem. Yes, I am still here.
Sorry.
Yeah, I just wanted to ask one final question, which was, what about applications for this framework? So one thing I can see is if you're able, so I think you mainly considered in this paper in painting and interpolation at the same time point, but Emil, you mentioned future time points as well. If you can do the same thing that an operational forecast system does, but more quickly, that could be very useful for, real-time applications. Are there other applications you see for this kind of setup?
Yes, I think it's capable, but we should be careful about input. You should be careful about the dataset. It, actually, in my opinion, usually one machine learning model is not totally applicable for different data sets. Usually we have to change something like parameter, hyperparameter, something else for different data sets. For our people, it seems like C size works, but if we change to another variable like C salinity or C temperature, it does not, I think, because usually the machine learning model is not totally applicable for everything. I'm not sure whether I'm right or not, but in my opinion, maybe it's true or not.
Okay, well, thank you very much for the thorough presentation. Thanks to everyone who participated. It's been really nice to get everyone involved in this seminar over the past year. It's been really gratifying to see the interest and the excitement and all the different ideas and what people have presented. We are now going to go on break from now to the holidays. We will be back sometime in mid-January. So I hope everyone has a happy and healthy holidays, and we will see you in 2021. Thank you.